Okay. Sorry, I just had a shocker of an attempt to start the recording, so we're restarting. We're doing chapter assignment number 7. Chapter 7 assignment. It's pretty late, so I might be a bit discombobulated, but we've already got our name and date and lucky number in the block and everything, so we'll go straight into it. Sketch 2 times 0.4 to the power of x. So, first things first, imagine that x is 0, right? And that'll answer this question actually down here. Let x equal 0. I've gone for a bit of a lighter pink, by the way. 2 times 0.4 to the power of 0 equals 2 times 1, because anything to the power of 0 is 1, equals 2. So if x is 0, it's 2, so this intercepts at 2. Bang. And then imagine x is really big, okay? If x goes really big, it's like 2. Let's not even go that big, actually. Let's just go like the power of 3 so far. Equals 2 times 0.4 times 0. Oh, wait. I'll leave that there. 4, 0.4. Right? And because they're less than 1, each time you multiply, it's like dividing by a number, right? Like multiplying by something less than 1, like 10 times 0.1, it gets smaller, right? So, by that logic, if we have more of these, if we keep multiplying, the more we keep multiplying, the smaller and smaller it's going to get as we go along the line. Which means, if we were to draw that in our graph, let's just start up from our 2 here. It's going to keep going smaller the further along we go, right? But here's the catch. It doesn't matter how far we go along, it'll be 2 times 0.4, which is a positive number, times 0.4 times 0.4. It's never times a negative number, right? These are all going to be positive numbers. So it'll be really small, but it's never actually going to get into this negative part. That's never going to go less than 0. And none of these numbers are going to be 0, right? They all have value. So no matter how small it gets, it's never going to equal 0. So we actually have something which is called an asymptote, which I don't know if you've learned about yet. There's no questions about it, so maybe you haven't. But there's an asymptote at y equals 0, because it can never equal 0, but it always approaches it. Now, on the other side of this 2, because it can have a negative value of x, it's going to keep going up, and here's why. If we have 2 to the power of 0.4 to the negative x, that is like saying 2 divided by 0.4 to the x, and the bigger this is, so the bigger this negative number is, or I guess the smaller the number is, the closer to negative infinity you get, you're going to be dividing by a smaller and smaller number, because like we just said, 0.4, the more times you multiply it by itself, the smaller the number is going to get, right? And if you divide by a really small number, let's say 1 divided by 1 on 1,000, it's 1 times 1,000 on 1, because that's how you do fractions, right? Equals 1,000. You're going to get bigger the smaller the thing you're dividing by is, right? So as long as it's below 1. So this is going to keep going bigger the further this way you go. So it looks like this. This is our shape. The value of our x-intercept, we've just established there is no x-intercept because this will never be able to equal or be below 0. So we can write NA or none or whatever you want to write. Or if you want to be mathematically correct, you can say no real x, but I reckon just say none. That's probably better. Domain. So the domain is just how far sideways it can go. Change color for this one. It doesn't matter what we plug in for x, it's allowed to go all the way that way and allowed to go all the way that way. It's just to keep going this way, you have to go really high up that way, right? But you can still do it if you go to negative infinity. So this is also, okay, this is going to be x's element of all real. x. The range, this can keep going up, obviously, to infinity, but this can't ever reach or go below 0. So y is greater than 0. And then end behavior, it's going from quarter 2 to quarter 1. And remember, this is quarter 3, quarter 4, just as a refresher. So Q2 to Q1. Perfect. Okay, next one. I might just erase this because it's creeping over. 2 times 4 to the power of x. So same but different this time. Apply the same theory in terms of how you like logically break it down, but different outcome. So let x equal 0. Good starting point. 2 times 4 to the power of 0 equals 2 times 1 equals 2. So it's going to intercept at 2. And then if we make it a really small number, it's going to be 2 times 4. Oh wait, I keep forgetting that this is an actual question, so we leave the 2 there. Make it a really small number, so as if it was down here. 2 times 4 to the power of negative 10 is 2 divided by 4 to the power of 10, which is 2 divided by a big number. Remember, this is just a sketch, so we don't need to work this stuff out properly. But we know it's 2 divided by a big number, which means it's going to be a really small number, right? So it's going to be close to our x-axis. And then we're going to come up, because it's divided by smaller and smaller numbers as we get closer to 0. And then we reach 0, and it's 2, because it's 2 divided by 4 to the power of 0, which is 2 divided by 1. Or just 2 times 4 to the power of 0, which is 2 times 1. Either way, it's 2. And then, if we go really big, it's 2 times 4 to the power of 10, which is 2 times a really big number. Obviously creeping very far across the boxes, but it means the further we go this way, the higher up we go. And it's in an exponential fashion, so it's going to curve up very quickly like that. And we have our shape. How many x-intercepts are there? Well, exact same thing. It doesn't matter what numbers you put in, it's never going to go 0 or below 0. So this is n/a or none. There are no x-intercepts. And our domain, it can go that distance that way and that distance that way. It can go to negative infinity and infinity, which means x is an element of all real numbers. Our range, once again, it can't be 0, it can't be below 0, but it can be anything above 0. So y is greater than 0. And end behavior, once again, it's going from Q2 over to Q1, Q3, Q4, and these are untouched. So Q2 to Q1. Perfect. Next one, 0.5 log x. Okay, so first I'll just quickly go over what a log is. If you have log a, b, well actually ax equals b, right? So you can pick whatever base you want for your log. It's saying a to what power equals x. So for example, you don't need a calculator for this stuff. If you have like log 2, 4 equals 2, this is a, this is b, right? So I'll actually just highlight to make it more obvious. Oh, that is a terrible color. I talk about making it more obvious and then I pick the worst color possible. That's terrible as well. Okay, you know what? I'm not going to highlight. Hopefully you can follow along. That's a, that's b, and that's, sorry, that's a, that's x, and that's b, right? I know this seems like it's taking ages, but if you can understand it, like I just showed with these other ones, if you understand how they work, you can just work out how the graph looks like for any thing. Then if we rearrange it, it's 2 to the 2 equals 4, and we know that's true. So that's just a simple demonstration of how it works. So with that knowledge in mind, let's launch straight into it. Log without a defined base, if it just has log and there's no a down here, you just assume it's 10. So this can be rewritten as 0.5 log 10x, which we don't need now, but is useful information. So let's just assume it's that. 0.5 log 10, that's let it equal 0, equals what? Well, 10 to the power of what is 0, right? That's what it's saying. Well, let's go over here. Let's try to figure out 10 to the power of what is 0. Well, we have an exponential graph, right? 10 to the power of, let's follow it along. Where does it hit 0? Oh wait, it doesn't, right? We've talked about that. Exponential graphs don't hit 0. So if you have that understanding of what a logarithm is, you can just say, okay, if we let it equal 0, that can't happen. So it can't actually pass, well, it can't be on this line. We know that for sure. What about passing this line? Well, can it be a negative number? If we replace this with like -3. Well, let's go over and look at this again. Does it ever cross into this zone? Nope. So we know that it can't be a negative number, which means not only can it not cross, it can't ever be in this side of it. So it's starting to look like pretty much the opposite of an exponential graph, right? If you understand these, it's really easy to understand logarithms, and that's why they get taught together as exponentials and logarithms. So if it can't be 0, then what can it be? Well, at x equals 0, here we have another one of those asymptotes that we talked about before, because it'll always approach it, but it'll never equal it. And then for what number will the answer be 0? Well, let's see. 0.5 log x equal 0. We can divide both sides by 0.5. And then the logarithm to oppose it, you put them both to the power of e to the power of 0. But another way, instead of doing that, you can just think 10 to the power of 0, right? And we've got an imaginary 10 down here. 10 to the power of 0 equals x, right? Because this is a, this is b, and this is x, like we were talking about earlier. And 10 to the power of 0 is 1. So x equals 1. So you can work it out algebraically like that, again, as long as you understand logarithms algebraically. So when y is 0, x is 1, which means along this line, it'll be 1. So 1. And erase this, and that is our x-intercept. So the value of x-intercept is 1. And what was the first, oh, sorry, put that in the wrong box. There we go, is 1. Value of y-intercept, well, we said it can't ever be 0, and it can't ever cross over this side. So this is none. There's no y-intercept. Next question, the range. Well, let's have a look. If we make it a really small, but not 0, because remember it can't be 0, it can't be over here. So let's make it like here, like 0.00001, right? What will the number look like? Well, log 10 equal y. 10 to the y equals 0.001. So 10 is a decently large number, but it's way bigger than 0.0001, right? So it's getting a lot smaller. So if we think about it this way, it's getting a lot smaller. It means it's moving down towards the negative side. It's becoming a very negative number, right? So it's going to be 10 to the power of negative, or I'll actually just write big negative number. So as you get to a super tiny but not 0 x number, it's becoming a really, really small y number. So it's going to be all the way down here. And then we're going to come up, and as we get closer to 1, it's going to come closer to 0 as our y number, right? Because we just established 10 to the 0 equals 1. It's getting closer to that, and it's going to hit 1 as it hits 0. And then what happens? Let's look at the behavior in this quadrant here. So let's pick a really big number. 1,000. Let's replace these numbers. 1,000. So 10 to the power of y equals 1,000. 10 is getting bigger, right? So how is the number getting bigger? Well, it's when it is becoming more positive as an x value. So draw that, replicate that here. We make it become more positive. So you get this sort of flip shape. If you draw them on the same graph, let's just copy this over. You can see it's actually, if it was drawn perfectly to scale, it would be an exact mirror of the exponential graph. So if you understand one, you understand the other, basically. But you have to make sure you understand it. That's why I'm teaching it and not just drawing it down. Because as soon as you do, like you can see, you can just figure it out yourself. So we've got our x-intercept. We've figured out that there are no y-intercepts. The domain, well, we know that it can't ever be 0 or negative. So x is greater than 0, and our range is y, all real, because you can keep going up and you can keep going down, right? Now, what you might find fascinating here is that this, that is a terrible color to pick, this, and pick another color, I suppose, this and this are exact opposites, right? When you go from exponential to log, you flip your x and y domain and range. So that aligns with what I was just saying. It is the exact inverse of the other graph. The domain gets flipped, the range gets flipped. Everything is just flipped perfectly. Now, end behavior, this is Q4, 3, 2, 1, and it's going from 4 up to 1. So we say from Q4 to Q1. Perfect. And then also I'm realizing I'm going to make this a separate video because it's taking a lot longer. I'll do the other questions in a second one, just like I did the chapter 6 assignment. Okay, and then our last one, sketch negative 2 log x. So before we start sketching anything, let's just think, what's different? Well, this 2 and this 0.5 are a little bit different, but that just changes how steep our graph is, right? So it'll look like, maybe not that sharp, but you know, it'll be a little more sharp than the other one. But a big difference is this negative. This negative completely flips it across the x-axis. So like if you take any y value, it'll just be the negative version of the x value. So let's look at it. So negative 2 log x equals y. Let's plug in, remember our imaginary 10 down here, let's plug in a really small number. And actually for the purposes of this, let's just ignore this 2, because it doesn't actually change that much, and you'll see why in a second. So 10 to the negative y, or I skipped a step there, log 10 negative y, which means 10 to the negative y equals 0.0001, right? Which means that y must be a big number because it's negative of big number equals big negative number. Sorry, I'm running out of room here if you can't tell. And we know that 10 to the power of something, being a smaller number, it has to be the power of big negative number, right? As we were just talking about. So y has to be a big positive number, which means when x is really, really small and close to 0, y is a big positive number, so it's up here. And then as x gets bigger, let's plug in same thing, big number, 1000, 1000, 10 to the power of negative y is 1000. It has to be 10 to the power of big right? A big negative number. Because you have a negative and then a negative equals positive number. I'm really hoping I'm making sense here. I've chosen this way to explain it because it means I can avoid like all the complex algebra, and hopefully it makes a bit more sense. So then we know y is going to be a big negative number. So we come like down here with my terrible drawing skills. So as x gets bigger, y gets bigger, and as x gets smaller, as x gets bigger, y gets smaller, it gets more negative, and as x gets smaller, y gets bigger. Yeah, sweet, so we figured that out. So we've sketched our shape. What point does it intercept? Well, it's let x equal 0. X is 0. Sorry, let y equal 0. Brain for it. Divide both sides by -2. 0 divided by -2 is still just 0, and then 10 to the 0 equals x. Oh, what do you know? It didn't change anything. So this point stays as 1, even though we've put a negative or a 2, or again, you could put 1000 in front of here. But once you let it equal 0, you can just divide both sides by 1000, and it still looks the same. You know, these two look identical. So when you're looking for the x-intercept of a logarithmic graph, it doesn't matter what you're multiplying the logarithmic function by, it won't actually change the x-intercept. So come over here, value of x-intercept, it's just going to be 1. Y-intercept, well, as we can see, it's the same thing. It doesn't cross into the other side, and that makes sense because if we took this shape, right, I'll just draw it actually instead of messing this up. Just redraw the same shape. Take that shape. This pink graph is just taking a number from down here and flipping it onto the top side, right? Because if you put negative in front of -1000, it turns into 1000. So it's moving it to the positive version of itself, right? So that is a big jump, right? That's a plus 2000 jump. So obviously it has a big space. It has a big space vertically between that point and that point. But then if you take a negative and put it in front of -1, it just equals 1. So that's only a plus 2 jump. So when you get really close at -1, you get a much smaller jump upwards, and that's reflected in the shapes of the graph. And then obviously that same jump happens here, but going the opposite direction. But you don't jump from a number that doesn't exist, like in the negative region, and like it doesn't suddenly become a part of the graph, right? So if you're just making the numbers the opposite version of themselves, it doesn't matter what numbers you're doing, they're not going to suddenly invent numbers on this side of the graph if there weren't any before, which means that, again, there's no numbers that equal 0 in this graph, and there's no negative x values. Domain, okay, well, it's the same domain, right? Because there's nothing in this side of the graph for either of them, which means it's just going to be x is greater than 0, and again, same range, because even though it's going in the opposite direction, it's still encompassing that same distance, right? It's just flipping it on opposite sides. So hopefully that makes sense. This is the way that was taught to me, and that stuck with me for a long time. So thank you to my older brother for that. And end behavior, final thing, we've got Q1, 2, 3, 4, and it's going from Q1 up here to Q4 down here. So Q4. I haven't checked the answers, so I might do that quickly actually, just to make sure I'm not sending you down the wrong path. But I am relatively confident that this is correct. Yeah. Sweet. All good. Look at us go, flying through this. I'm proud of you for all the studying and hard work that you're putting into this. I'm glad that the videos are helping. I will finish the rest of this, don't worry. It's just going to be in a separate video.